electronegativity. We talked about that a little bit at the end of the last chapter when we were talking about Linus Pauling and the Pauling electronegativity scale as being one of our atomic trends. Right? So the electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. Linus Pauling's method of determining the values of electronegativity. So for an example, Hx, the relative electronegativities of the hydrogen and whatever X is, usually that's going to be a halogen, are determined by comparing the measured Hx bond energy to the expected bond energy. So you expect a certain bond energy, and then you look at the difference between, you look at the sum of the hydrogen-hydrogen bond energy and the XX bond energy, like a chlorine-chlorine bond energy, and you divide it by 2. Okay? So how do we know if these electrons are going to be shared equally? But I am not going to make you compute this. This is just where it comes from. I will give you a table that will include all of your electronegativity values. Okay? How do we know these electrons are going to be shared equally or not? Well, our more electronegative elements are going to attract electrons more strongly. So it's a relative scale. It's related to the ionization energy and the electron affinity of the atoms. It's going to be unitless. Our element with the smallest electronegativity is cesium, Cs. And the one with the largest electronegativity is going to be fluorine with an electronegativity of 4. So if you think about where these guys are, right? Cesium, right? Alkali metal, bottom left-hand side of the table, really does not want to pick up an electron. Big fluffy, it's a big fluffy atom. It's got this one extra electron. It's not holding on to it very tightly, right? You know, imagine it's a big old beach ball and you're trying to give it a hug and your arms won't fit all the way around. And so it's not going to hold on to that electron very tightly because it's got so many inner shell electrons, right? So it's very willing to give up that extra electron. Fluorine, on the other hand, it really wants to pick up an electron. So it's going to be our most electronegative atom. It wants to gain an electron to make that noble gas configuration, to make that octet. So this is coming from Pauling. So here's a picture of Pauling, early Pauling and old Pauling, back when if you couldn't wear a beard, you got yourself a corncob pipe. He's missing the bow tie. So in high school, Washington High School in Portland, they gave him the diploma 45 years later after he had already won 2 Nobel Prizes. So if you think your high school was tough, just think about how hard-ass his high school was when it's like, I don't know, Linus, he got 1, but maybe, no, we got to wait, man. So he's got 2 Nobel Prizes. He's one of a very few people to have 2. He traveled to Europe on the Guggenheim Fellowship to study under Sommerfeld in Munich, and he studied under Bohr and Schrödinger in Zurich. He was a pioneer in biochemistry. He almost had the structure of DNA down. He was like this close. So he knew like it was made out of like a carbohydrate backbone, a ribose backbone. And he knew it had like these base pairs to it, but he kind of had it going the wrong way with the base pairs pointing out instead of pointing in. And then once he kind of got burned with that, he's like, okay, I'm going to do some work with proteins, but he would need 2 kilograms of a protein in order to do anything. And if you've ever done stuff with like cell and molecular biology, or if you want to, you know, you're talking about like nanograms, sub-micrograms of protein that you're able to express if it's something interesting. If it's like bovine serum albumin, then that's super common, or ubiquitin. You might be able to get a couple of kilograms of that out. But most of the interesting proteins, very, very small amounts, but you couldn't do analysis with small amounts because they didn't have the analytical chemical tools to do that biochemistry. So you needed a lot of that protein. We can do things with much smaller crystals now. If you're going to do crystallography, we can do a lot more stuff with mass spectrometry than we were able to do, especially on smaller scales. Towards later in life, he really became obsessed with the idea that vitamin C was like a universal cure-all. And so part of the whole hype surrounding vitamin C use comes from Pauling. So to determine our electronegativity, we're going to look at the delta or difference between the actual and expected bond energies. We can calculate that using this formula. If our difference right? Between H and X, they've got identical electronegativities. Their shared electrons are closer to the X atom if the electronegativity of X is greater than X. So our charge distribution basically is going to look like I've got something that's got a positive, less electronegativity, and my partial negative, this little tiny delta, means partial. Right, I've got a partial negative charge over here on whatever my halogen is, or something that's got a high electronegativity. Right? My electronegativity scale, they like to print this guy in 3D. Down here with cesium and francium down at the bottom left, very low electronegativity. They don't want to pick up an electron. Over here on the upper right-hand corner, you've got fluorine. It wants to pick up an electron. So this is going to follow some of our trends that we've already seen with atomic properties and atomic periodicity. Right, the important thing to know is that, yeah, generally upper right-hand corner, high electronegativity, want electrons, bottom left, do not want electrons, want to give them up. Now there's some irregularities to the trend, right? You see some humps going on here with these transition metals, right? Those guys are weird. One of the other things to watch out for too is things that are going to have the same electronegativity. So generally electronegativity is going to increase left to right and it's going to decrease top to bottom. There are some places where our electronegativities are the same, like carbon here at 2.5 and sulfur also at 2.5. So a bond between carbon and sulfur is going to be completely nonpolar. And what our electronegativity difference is between element 1 and element 2, right? So sodium and oxygen, or between cesium, or between carbon and sulfur, or between boron and manganese, is what's going to determine whether something is going to be ionic, where we have, quote, full charge separation, whether it's going to be polar covalent, where we've got partial charges between one atom and the other, right? Partial charge, a positive charge on one and a partial negative charge on the other, or whether something's going to be nonpolar covalent, where we've got a symmetrical charge. Right? Polar covalent bonds, you're going to have an unsymmetrical electron distribution in which the bonding electrons are attracted more strongly by one atom than the other. And so we've got a relationship between the electronegativity and the bond type. If the electronegativity difference between the bonding atoms is 0, right, it's going to be a covalent bond. So our covalent character is going to increase as we get to electronegativity differences that are close to 0. If we've got a slight difference between them, it's going to be intermediate difference, and it's going to be a polar covalent bond. If you got a large difference between our electronegativities, you're going to form an ionic bond, and you're going to have more ionic character. Note, you can have a 100% covalent bond, right? 100% equal sharing. If I look at something like H2 or O2 or carbon and sulfur, those are going to be completely nonpolar, 0 electronegativity difference. Those electrons are shared even Stevens, 100% covalent bond. You cannot have a 100% ionic bond. The reason being is that those electrons have to spend some time around both atoms in order for that bond to exist. So it might be for something like sodium chloride, right, spending 99% of its time around the chlorine, or electron spends most of its time around the chlorine and very little time around the sodium, but it's going to spend some time around the sodium. We've got this field here that's representing our electron density. Right? The color is going to represent whether it's more electropositive or electronegative, red for negative, blue for positive. And so it's still sharing a little bit, even though this sodium's got this very large, practically complete +1 charge. Right? And something like HCl, hydrochloric acid, you've got a polar, and this is in the solid form, not when you dissolve it. When you dissolve it, it's going to completely dissociate into ions. But if you've got this solid, you've got to have a partial positive and a partial negative. And so the bond between the hydrogen and the chlorine is a little bit sharey, but it's still uneven. This chlorine is going to take a lot more of the electron density. The electron's going to spend time hanging out over here and very little time hanging out over on the hydrogen. So our hydrogen's got a plus partial positive, our chlorine's got a partial negative. This is going to form a polar bond. In complete even sharing, right, we've got a non-polar covalent bond like chlorine, dichlorine, so Cl2, right? Completely even Steven sharing, right? Everybody is the same. Their electrons are going to spend the same amount of time around one chlorine as they do around the other because the electronegativity difference is the same, right? It'd be like two twins sharing stuff. So how do our electronegativities relate to bond polarity? We've got a numerical way to do this. So stick this in your head because this is what makes something a polar bond versus a nonpolar bond versus an ionic bond. So the stuff about it's between a metal and a nonmetal, or between two nonmetals, between a metal, this is it, right? This is what that rule is. And it's kind of an arbitrary rule, but if your electronegativity difference is 0, you are nonpolar. If, like in hydrofluoric acid, your electronegativity difference is between 0 and 1.9, you are a polar covalent bond. If your electronegativity difference is 2 or greater, you're going to be a ionic bond. All right, so it's this electronegativity difference that is going to determine whether you are polar, covalent, nonpolar, or an ionic bond. So now we have got two ways to take atoms and put them together, right? We've got the tools to stick atoms together. Once we start sticking atoms together, we are able to make molecules, right? So once we put two atoms together, we got a molecule. We've got, just like we've got a polar bond, we can sometimes get polar molecules. Polar bonds often result in polar molecules. A polar molecule is something that possesses a dipole. So those are those molecules that are able to orient themselves in a magnetic field or an electric field where you've got a partial positive end and a partial negative, and there are lots and lots of polar molecules. Water, for example, is a polar molecule. When we talk about hydrophobicity versus hydrophilicity, is something water loving or is it water fearing? Is something a fat-soluble vitamin? It's hydrophobic, it's nonpolar, or is it a water-soluble vitamin, like the ones that turn your pee yellow, right? That's going to be a polar molecule. That's a polar vitamin. It's going to be soluble in water. So solubility is going to tie into our polarity of our molecules. Oil and water are not going to mix because they have different kinds of polarity to them. Okay? A molecule with all nonpolar bonds is always going to be nonpolar. Molecules with polar bonds can either be polar or nonpolar, and that's going to depend on their three-dimensional shape, their geometry, and we'll talk about that when we do Vesper. So the first thing we need to do is look at the dipole moment for our molecule. And it's just a quantitative measure of a dipole. Well, what's a dipole? A dipole is just how unevenly are we distributing the electrons across an entire molecule. So we can get a dipole moment in each bond, right? And then that's going to be related to the charge and the distance. So how far apart are they and how big that charge is, right? The units are going to be coulombs times meter, or it's going to be given units of Debye. Debye was a guy who did a lot of physical chemistry and analytical chemistry. So he gets the unit D, Debye, and 1 Debye is 3.34 times 10 to the minus 30 coulombs times meters. Right, if we look at the polarity of the bonds between HF, HCl, HBr, and HI, so these are halogens, right? You will notice that there is a trend. This HF is going to be way more polar than this HI. So iodine is not pulling that electron as close to it as the fluorine is, right? You think about that as having the same charge, right? Iodine and chlorine are both going to be -1, but iodine being big and fluffy, that bond radius, the distance between those two nuclear centers, is going to be bigger for iodine than it is for fluorine. Fluorine is small, it's hard, it's got that negative charge to it. Iodine, big and fluffy, it's not going to have the same uneven distribution of electron density. Right? So we can order the following bonds in order of polarity: HH, OH, CLH, SH, and FH. Right? We need to do that. We're going to look at the electronegativity differences between them. The polarity of the bond increases as the difference in electronegativity increases. From the electronegativity values on our chart, we're going to look at the bond polarity that we're going to expect. So an HH bond is 2.1 to 2.1. Our electronegativity difference is 0. Between sulfur and hydrogen, it's going to be 2.5 and 2.1.4. Between chlorine and hydrogen, it's going to be 3 and 2.1, so 0.9. Between oxygen and hydrogen, 3.5 minus 2.1, it's going to be 1.4. And between fluorine, our most electronegative element, that's going to be 4, and hydrogen, 2.1, we'll end up with 1.9, almost an electronegativity difference of 2, so it's going to be almost ionic in terms of its character. If lithium and fluorine react, which one has more of attraction for an electron? It's going to be fluorine. Why? Because that fluorine is the most electronegative atom. In a bond between fluorine and iodine, which one has more attraction for an electron? Fluorine again, because it's got the larger electronegativity. So the general trend for electronegativity values across rows is that it's going to increase as we go left to right, and as we go down the column, it's going to decrease. Right? So as we go from lithium, and then we go down to francium, right? Lithium is going to be more electronegative than francium is going to be. That's because you've got atomic size that factors into it. Things on the left-hand side are more willing to give up an electron to form that stable octet. Atoms on the right-hand side of the periodic table, particularly our halogens, want to pick up an electron to form that stable octet configuration. Which of the following bonds would be least polar, yet to be considered polar covalent? So we've got magnesium oxide, carbon oxygen, oxygen, silicon oxygen, and nitrogen and oxygen. The tricky part here is we got this oxygen-oxygen bond, which is covalent, but it's going to be a completely non-polar covalent bond. We need to look at the electronegativity differences between the others. Oxygen is going to have an electronegativity of 3.5. Magnesium is going to have an electronegativity of 1.2. Carbon is 2.5. Silicon is 1.8, and nitrogen is 3. So the one that is going to be least polar but still be considered a covalent bond will be the silicon-oxygen bond. This magnesium one is a little bit too much. This oxygen-oxygen bond is a little bit too little.